Thank you, Bernard. So before I start, I want to say that I think that dragons are pretty cool, and maybe you will agree with me if you watch Game of Thrones. So at the University of Liège, we started to experiment a bit with a kind of machine learning, so convolutional neural network. First, as part of the master thesis, so it's actually Pierre-Olivier Van Back did most of the work that I will present. So there's a first foray there to see if it's interesting for us for our application on the longer term. So at the University of Liège, we do a chronography. So focal plane wavefront sensing is one block of the overall wavefront control, let's say. So it's optically simple, but can be completely a bit complex. And of course, the mapping between your pupil plane and your focal plane intensity, well, it's nonlinear and can be degenerated. So maybe you are familiar with this, but let's just remind you that, so at least there are two challenges, the twin image problem. So if you have a complex value objects and its complex conjugate, they have the same Fourier modulus. So in practice, that means, for example, that even modes will have a sign ambiguity. So if you have plus or minus focus, you get the same image in the focal plane. So that's why you will need, for example, phase diversity. Another challenge can be what's dubbed the capture range problem. So that's basically the likelihood of your algorithm to stagnate in a local minima. And this problem gets worse if you are trying to estimate larger wavefront error and if you are trying to estimate more coefficients. So we started a bit this work to asking ourselves, do convolutional neural network can do for us, and is it a nice avenue to explore in the future? No. You have to be patient here.
Yeah, it's the same.
So, what's the
Je sais que j'étais unplug et replug, peut-être.
Okay.
I think you want it, I think it's just plug it into the power, right?
My computer.
It's only that it
Ça avance une slide là.
Okay.
Mais le power.
So machine learning has been around actually since a while, and in the 90s, probably that was the first time there was a big hype about that tool. It was used more or less successfully, and there actually was even some experiment on Sky, well, offline experiment, but in parallel taking Shakardman measurement and measurement with in and out of focus using a neural network. And they get some agreement on the very first Zernike modes. And so most of the work that has been done, and actually the last talk was using a similar architecture, is this multi-layer perceptron model, where you have an input layer, a hidden neural layer of neurons, and then an output layer. So for example, those early works use here directly the image, so they give the pixels as input. And the neurons there are just a linear combination with some weight, and then you apply this activation function that introduces some nonlinearity here. And actually, a recent work that motivated us a bit is a work from Payne and Finnep, where they look at what CNN can help us for GWST, and essentially actually to solve this capture range problem. So the one with having very large aberration here, and they wanted the CNN to provide the initial input to more classical algorithms. And so that's what you get here in this figure. The dashed line is classical optimization gradient descent, and so it quickly saturates and they can't retrieve it or correct. And while if they use this machine learning input, they get something much better, and so they extend the range of operation. And they use, I'm not going to go in details, but they use this CNN from Google called Inception version 3 that we also use afterwards, among others. So it's only simulation that we did. So we generate different data sets, one with 20 and the other one with 100 Zernike modes. We assume some kind of spatial PSD typical, with about 1 radian of error, actually a distribution of it, but with a mean of 1 radian. We generate a big data set, and in and out of focus, and we injected a bit of photo noise, but admittedly this is very high signal to noise. So we then actually selected a couple of architectures that we wanted to compare. So those are the architecture we have considered, and they all rank pretty well in image classification contests. So annually you have this big library of image where you then can try to recognize a cat or mushrooms or something like that. And those have been very powerful in doing those over the years. And we tested them. So some of them we use them to actually directly estimate Zernike coefficients, and the other one we use them to estimate directly the phase map. So it's a bit different approach. Again, I'm not going into in detail of that one, but I want just to present a bit of this one. This one is called a U-net because it's from a U shape. And just so that you get a little bit of sense how it works, and not that it's only a black box. So here you have either 1 or 2 images as an input, and the output is your phase map. And what happens is that you have a downsampling part, then a bottleneck, and an upsampling part. And that relies mostly on convolution kernels, which will extract feature from your map. So the first step is from this 1 or 2 images to create 64 maps. That means you will have 64 different kernels that will extract different kind of features. And so the parameter of this model, most of the parameters are the numbers in this kernel. And so you do this convolution, then you do a downsampling that's done typically by max pooling. It's pretty simple. And then you go down, and you each time double the number of features you're having. And then you upsample, so that's kind of the same operation for you have also convolution there, and then you have skip connection. So that means you use the feature map here on the left part to the right part. And so that gives you both, in a way, localization, so the localization of specific feature on the left side, and context, in a way. So that's something that has been developed for biomedical application, and for image segmentation, actually. So that's exactly what we're... so you train your model. Can take a lot of time. This is not specifically optimized, but for example, if you take 100 images, you can wait quite a while, so you can daydream on some beautiful picture created by machine learning, examples. And then you can compare the results. So that's just showing here on 21 Zernike modes the different architecture we've been considering. And so, well, the first thing is that all basically works relatively well. Now you can look at the results and you can compare them. Maybe the only thing that's interesting here is that the error is more or less uniform between all the modes. You can look at the phase map and then compare the one that gives you the Zernike coefficient. So obviously there, the results are smooth, where if you have direct image estimation, well, you get some fine-grained structure. But actually, this direct estimation technique gives us slightly better results. So here you have this histogram compare 4 of the architecture for our 2 cases. And basically, with an input of 1 radian, we get a factor of 100 improvement with 20 Zernike, and a factor of 10 or so with 100 Zernike. Then, well, it's all easy so far. And the big question is how robust that might be, and ultimately how useful it might be. One thing is how does this CNN works when exposed to something outside your training range. And obviously, that's if you train it in a narrow region, it's pretty effective in that region, give you high performance, that's the green part. But it quickly decreases outside of that range. And you can make it more robust and slightly more performant. I mean, it's relatively obvious. Then you can look at noise. So here it's only photo noise. So we train at only a specific signal to noise and then look what it looked like. So it quickly decreases in this case. So it's not very robust. Now again, you could have a smarter strategy and expose it to more photo noise, for example, at the expense, obviously, probably on a bit of performance. Then we also look a bit at comparing this with a classical phase retrieval algorithm. We use this one, hybrid input-output. So it's really only scratching the surface, but it shows you that, yeah, well, the HIO, of course, is iterative, so it can take a while. Sometimes it converges, and when it converges, usually it gives you a much better performance, much better results. Sometimes it doesn't converge. And so maybe here there's a nice combination to have a bit like Payne and FinUp have been doing. So you could imagine to use a CNN to have a first starting solution, and then you run your iterative algorithm. Then the next step I've been recently looking is a bit what we get behind a chronograph. And you may know it in Liège, we have our a nice precious device made out of synthetic diamond. So it's a zero order grating that is engraved into diamond. And that introduces so a phase ramp at the focal plane. And so basically you have a singularity at the center, and nature doesn't like much singularity, so it diffracts the light outside of the pupil. And so for a circular aperture, you get the perfect chronograph. So that would be your Leo plane, and you just block it. So my 2-cent interpretation is that that device removes basically your airy pattern, and what's left is just your residual aberration. Now, if you consider annular aperture as not perfect anymore, so here you will have your pupil intensity. Here it will be the Leo intensity, and then that will be the focal image. So you get this donut or something like this with some aberration that look like the shadow of a black hole. So we've seen this a long time before. Yeah, so the idea now, yeah, can we apply this architecture to our post-chronographic images, and how does it perform with respect to PSF? So we look at much lower aberration, so at 50 nanometer wavelength error at the 2.2 micrometer, considering an annular aperture and only one single image in focus. And so I just done this small exercise here to look what is the standard deviation on my modes. So I look here at 21 modes. Here it's an infinite signal to noise. So you have here what is injected, actually. So it's following my power law. And then basically you can see here you have substantially the same results, which, okay, makes sense as well. Now, if you start to decrease the signal to noise, then you see those even modes popping up. So you have tip tilt, focus, astigmatism, and this is the next even modes popping up. So you see that in a PSF case, normal imaging case, well, of course, you hit this degeneracy somehow, and it gets worse there, and you can further decrease the noise. And this stage is very clear that basically here the CNN doesn't estimate anymore. But what is interesting is that it's not that this one time is performing a good estimation and the other time doing the opposite in sign, is that it knows that there's some kind of ambiguity and it estimates something that is very low. So it's behaving relatively well comparing this degeneracy, I would say. I haven't looked at it yet, and there might be degeneracy here on the post-chronographic PSF, but it's not so clear analytically with an annular aperture, so but it remains to be investigated. But it behaves much better until here. So yeah, that's about it. I just wanted to mention that it's a very fashionable trend at the moment. I don't know if it's for good or bad. So there's a lot of paper popping up outside of astronomy and as well in astronomy. So maybe it's good to keep this in the radar. And yeah, so I think the question here was quite simple. Is it worth considering? I think yes. There's more to be investigated here. And maybe the perspective is combining this with other techniques. The post-chronographic PSF is certainly interesting if it can work with a single in-focus images, because then you could directly use it with scientific images. And the behavior with this twin image problem and the stagnation is interesting to investigate a bit more. And of course, there's a lot to investigate in terms of robustness. I haven't considered residual atmospheric turbulence or other modes that the network was not trained for. So, and then you want to go in the lab and see as well what other machine learning tool might offer you as technique. Yeah. So that's it. And there's a lot more that you can do with machine learning, combining your favorite hobbies, for example. Thank you very much.